Hello everyone, welcome to this talk entitled On How Turing and Singleton Arc Consistency Broke the Enigma Code. This is joint work by Valentin Antuori, Tom Portoleau, Emmanuel Hebrard, and myself, Louis Riviere. This work is following the hackathon that took place during the ICP Summer School um, in 2020-2021, in which participants had to model the Enigma machine in order to decipher messages. Um, so for this presentation, we will first talk about the Enigma machine. You've probably heard of it, and how we model it using constraint programming. Then we will talk about the bomb and its relation to singleton arc consistency. And finally, we will see some experimental results. So the Enigma machine was commercialized starting 1923. There are many different um, versions of the machine with different tweaks, but in this presentation, sorry, we will consider a simplified version of it. The machine was used during World War II by the Germans to encipher uh, messages, and famously, Alan Turing and his team at Bletchley Park worked on deciphering those messages, and its efforts are said to have substantially reduced the length of the war. Overall, in this picture, you can see the big vision of the Enigma machine, how it works. So uh, first, you have an input, so you type a letter on this keyboard. A signal is sent through the plugboard. The plugboard is switches letter according to the chords. We will see it more in details later, which the signals then go through three rotors, which are the moving part of the machine, which makes it hard to decipher, then through the reflector, and then back through the same rotors that before, the same plugboard, and finally on a light bulb display that indicates to which letter the letter you pressed is encoded to. The whole machine can be seen as a function that takes the output text and with the key or the state of the machine composed of the initial position of the rotors as well as the different chords used in the plugboard gives us the ciphertext or the output text. So the plugboard can be seen as a substitution cipher, so substitutes one letter to another letter. In this example, there are two chords. The first link is from letter A to letter J, and the second link is from letter S to letter O. This means that if you type an A through the plugboard, the letter A will be turned into a J, and so on. There is a known number of patch chords, which is L, which makes this whole substitution a symmetric permutation with 26 minus 2L fixed points letter encoded to themselves. So how do we model this using CP? So first we have an array of variables, the plugboard. Each variable indicates uh, to which letter the input letter is encoded to. So for example, plug A is a variable indicating to which letter an input A is translated to through the plugboard. And this is represented with an element constraint, um, signifying that if the input is a letter, then the output must be another letter. Um, we use the constraint all different to ensure that it is a valid permutation of the letters. There is also a symmetric constraint. So if letter A is encoded to letter B is encoded to letter A. That is due to the nature of the plugboard. And we also have the constraint for the fixed points. So we have the number of fixed points that must be 26 minus 2L. Then we have the rotors. So the rotors is again a simple substitution cipher, and these do not change. They are not variable, these substitutions. But what happens is that these rotates. Uh, Indeed, at every keystroke, the fast rotor, the first rotor here, rotates one step, and at each keystroke it rotates one step, and after 26 steps, the medium rotor rotates one step, and after 26 steps of the medium rotor, the slow rotor here rotates one step. And this makes it so that the same letter encoded twice may not encode to the same letter, or may, but it does not necessarily encode to the same letter twice. That makes Enigma hard to decipher using traditional deciphering methods. So as an example here, we will see on a simple alphabet of 6 letters. In these pictures, what you see is first the fast rotor, the medium rotor, and the slow rotor, and the reflector in the end. So you can see that if you press the letter A in the initial position of the rotors, or this part of the Enigma machine, it is encoded to the letter C. After one keystroke here, you can see that the first rotor rotated 1 step. You can see this link here went up 1 step, and it is now encoded. The same letter A is encoded to letter B. After 2 strokes, it is encoded to letter B again, and so on and so on. The first rotor rotates until you reach the 6th keystroke, where the first rotor rotates, but also the second one, the medium one, rotates 1 step, and then only the first rotor rotates, and so on and so on. So how do we model this using constraint programming? So for each rotor, we have 2 variables, the input letter and the output letter. We have an element constraint to link the 2 variables, but on top of that, we have a variable corresponding to the offset of the rotor. So this is composed both of the key, so the initial position of the rotor, plus an increment for each keystroke. Overall, we have this constraint, which signifies that, so we add the offset to the input, modulo 26 to stay within the domain of the variable, and then we access this permutation table. And then, of course, when the rotor rotates, it rotates both um, with regards to the input, but also to the output in the other direction. That's why we have to subtract the offset in the end, and again modulo 26 um, to stay within domains of the variables. Finally, we have the reflector. So the reflector is a simple shift position cipher again, with the additional property that it is symmetric. So if letter A is encoded to letter B is encoded to letter A, and it is anti-reflexive. Letter A cannot be encoded to itself, and this makes the whole Enigma machine anti-reflexive. So overall, we have for each letter uh, in the plain text a variable xi0 for the position I in the plain text, and then um, at every step of encryption, we have a variable representing the internal letter at this step of the encryption until we reach the output letter xi10, which is the letter at position 10 in the ciphertext. So this allows us, if we fix the input letter, the key, and the plugboard, to simulate Enigma by running the constraint programming model. Or if we fix the input letter and the output letters, we can try to find compatible keys of offset of the rotors and plugboard assignments that are compatible with such input and outputs. And this allows us to decipher messages. But this necessitates an input letter. Alan Turing and his team also tried to guess some plain text in order to find probable key and plugboard assignments to decipher the rest of the text. And this is called a crib. For example, let's assume that we know that constraint is in our message and it is encrypted to this message. Then we can fix the variables for the position, the first letter in the plain text to C, and the first letter in the ciphertext to I, and we can try to solve the model to find probable key and plugboard assignments. And these information form what we call a menu. In this graph, you can see that for each such pair, we have an edge signifying here that at position 0 in the message, C is linked to letter I, and that will be useful later. So again, for every letter of the input message and the output message, we have this kind of picture with mostly element constraints linking the different variables, which are parameterized for the rotors by the key, the offset of the rotors, and parameterized by the plugboard links in the plugboards. This can already be used to decipher messages. But Alan Turing had a smarter way to do it, and this is what we will see next. This is called the bomb. So the bomb was the device developed at Bletchley Park by Alan Turing and his team. Um, so how the bomb works is, well, it's for a large part composed of many Enigma machine, or it's capable of simulating many Enigma machine for a given key and trying to find compatible plugboard assignments um, with a crib and a ciphertext as inputs. So how does the bomb work? So assuming a given key, you can see the whole process of the Enigma machine at step I um, as composed of three parts. Um, you have first from the plain text or the input letter a transformation to another letter through the plugboard. Then you have this the three rotors and uh, the reflector at step I that you know if you have a key, and that turns this letter into another, and then you have the plugboard back, which gives you the output letter or the ciphertext letter. So you are trying to find information about the plugboard by getting a key. So for example, you can take every edge of your menu. For example, if you have letter A that you know is encrypted to letter C through the whole Enigma machine at step I of the the plain text and the ciphertext, you're going to guess that maybe through the plugboard, uh, letter A is linked to letter B. Because you know the key and you know it's at step 6, you can compute the action of the rotors and the reflector, and you know that it would give you the letter R if you have B as an input. And then because your output is C, uh, you have the new information that if A is linked to B, then it must be that R is linked to C in the plugboard. And you can continue that action for every edge in your menu. For example, here, if you have the letter R as an input, you guessed before that it was linked to C. You can compute the action of the scrambler at step 5 that gives you the letter N. So it must be that N is linked to letter T in the plugboard. So you continue this so on and so on until you either find a contradiction. So it means that one guess you made was wrong, or you find no contradiction, uh, and that means that you have found a compatible partial plugboard assignments with the key you tried. This is called a stop, and once you have a stop, you can try to decipher the rest of the message with the key and the plugboard assignment, and if it's not gibberish, then you have found the message. So this is what Singleton Arc Consistency does. We first assume a key, so this remove the parameter key from the element constraint in the rotors, and then Singleton Arc Consistency will try every possible assignment of a pair for A. Arc Consistency will simulate the scrambler and check if it is consistent. If it is not consistent, the letter will be removed from the domain of the possible match for A. So SAC discovers every connection the bomb does, sometimes a bit more, because the all diff constraint on the variables considers every letter, in particular letters that sometimes are not in the menu. Finally, we ran some experiments using random text from Wikipedia and enciphering them using historically accurate rotors. Um, we used a crib of size 12 with different number of cycles in the menu and the number of nodes in the menu ranging from 9 to 16. Some menus have too many solutions, in which case they could not be solved, and those sometimes were discarded in the instances. And so the two methods we compare are Choco alone, the first model we presented, and the same model with the addition of Singleton Arc Consistency that we talked about earlier. The results clearly show that um, using SAC allows to solve many more instances, um, and it can be interesting to note that the number of fail plus the number of stops for Choco plus SAC exactly equals 26 to the power of 3, which is the number of key tried. So for each key, either a fail was encountered or it was a stop. And finally, in this graph representing the cumulative probability of uh, solving the code in less than X seconds with a 1 hour timeout, showed that for easy instances, it might be preferable to use the Choco solver alone, but for bigger instances, using singleton arc consistency greatly improves the model, going from 60% instances solved within an hour to 99%. As a conclusion, SAC is pretty much the bomb. I hope you enjoyed this presentation. If you want more details, there are many details we went over in this presentation because it makes the model more complicated and it's not necessary to understand what's going on. But you can check out our paper if you desire more information. Enjoy the rest of the conference and goodbye.